So, a light year is the distance light travels in a year. Pretty intuitive, which is just over 9 trillion kilometers or 5 trillion miles. And this is used instead of using like, say this star is so many miles away, because it's something we can't really understand very well. So we put it in terms of light years instead. That's a little bit more manageable. And then the next thing we use is kind of a standard measurement. It's for masses of objects in space, called a solar mass. And this is the symbol here, which is 2 times 10 to the 30 kilograms, or about 4 times 10 to the 30 pounds. And so this is used to have us have kind of a reference for the masses of stars and other objects that based on something that we're familiar with, being the sun. And then this here is kind of what I'll be covering today in the remainder of the talk, the different, how different nebulas are structured, and then different phenomena we see in nebula. So let's define what is a nebula. So the word nebula has its roots in Latin, and it means mist or cloud. Obviously, these objects are found in outer space, and they are composed of about 90% hydrogen gas. Most of the rest is helium, and there are very small amounts of slightly heavier elements such as oxygen, carbon, neon, nitrogen, etc. And it's interesting because people in the early days of astronomy thought galaxies were nebulas also, because telescopes weren't that high powered back then. Things just looked fuzzy that were really far away and very detailed. So it was difficult to tell what kind of was a nebula for certain, and what an object, what it could be something else. So kind of going in with that, so in the early days of modern astronomy, so after say 1750 or so, a hot topic at that time was looking for comets. So Charles Messier was a 18th century French astronomer, and that was his main goal in his career. So every night he would take out his telescope and look through the sky, and he identified fuzzy objects. So like I said, some of them were galaxies, some of them were nebulas, some of them were star clusters. And so he didn't actually end up finding any comets, but we do have this catalog now that he kind of started, that we use to look at interesting things in the night sky. And then a couple years later, William Herschel kind of had the same idea. He published his catalog of 2,500 of the same type of fuzzy objects, those being star clusters, nebulas, and galaxy. And then William's son, John, added over 2,000 more, and most of those were in the southern hemisphere. And so the Herschel's catalog formed the basis for what we use today to classify objects in the night sky, the New General Catalog. So you'll see me reference actually both Messier's catalogs and the New General Catalog in the rest of this talk. And so the next biggest development in the discovery and understanding of nebulas was a telescope slash camera formed by Bernard Schmidt. He kind of took the design of a telescope and modified it. So instead of having a mirror here reflecting out to an eyepiece, he instead inserted a photographic film that allowed for long exposure images of objects in the night sky. And the reason that's important is because long exposure images and photographs allow us to capture more detail than our eyes, the naked eye, can detect. So that led to the beginning of our understanding of the difference between a nebula, a cluster of stars, and a galaxy. So spectroscopy is how we determine what elements are in nebulas. And this is really important because we can determine not just what's in the nebula, but what that might say about how the nebula formed, and things like that. So the way spectrometry works is, say we're looking at a star in the night sky. So then that comes in and bounces off a grating, which acts like a prism that splits up the white light from the sky and splits it into a spectrum. And then the way we know what elements are present in an object is because we have done spectrographs with individual elements down here on Earth. So we know what bands here are sort of supposed to show up for what elements are present. So for example, nitrogen. So the way spectroscopy works is atoms get excited by an incoming photon, an incoming particle of light. And so as the atom de-excites, it emits another photon. And these photons are at certain wavelengths, because quantum physics is weird, because energy is quantized. And I can go into that later if we'd like. But for now, suffice to say that every chemical element has a specific kind of pattern that shows up when you point a spectrograph at the element. So then when we combine all these together, so for example, say this line of nitrogen here is this one. So then we can say, compare it with the rest of the spectrum and tell, hey, there's nitrogen in here. And then we can look for this specific pattern, and in this whole, the whole spectrum that we see, and say, hey, there's carbon in here too. And that's how we know what elements are in a nebula. So let's go on to the origins of nebula. I'm going to talk about 4 types today. And so the first type is what's called a planetary nebula. And here's an example of one. This is called the Ring Nebula. So to find it in the sky, you would find this star, Vega. So Vega is the brightest star in the northern hemisphere in the summertime. So say you were outside at night in July, and if you were to look straight up, you would see Vega. Although it's not easy, or rather, it's not hard to miss, because, like I said, it is the brightest star. So then, once you've found Vega, you would look for this trapezoid shape next to it. And then between these 2 stars that are farthest away from Vega is where the Ring Nebula is. So planetary nebulas in general come from stars about the size of our sun to about 8 times the mass of our sun. So in 5 to 10 billion years, when our sun reaches the end of its life, it will turn into something similar to the Ring Nebula. So how does this happen? So a planetary nebula occurs when a star reaches the end of its life, and its sort of atmosphere starts cooling down and therefore starts to expand outwards. And in the center is right here, this one's just a background star, but this one in the middle is a white dwarf, which used to be the core of the star. And interestingly, the white dwarf, even though it's really small, lights up the entire nebula so that we can see it. And so planetary nebulas in general are named for their appearance. Back when they were first being categorized, because the telescopes weren't that great, they looked fuzzy. So I think one astronomer, I forget who, but they described it as a really faint Jupiter when they were looking at the Ring Nebula. So that is where they get their name, but their name, the Planetary Nebula, has nothing to do with the planet themselves. It all has to do with the star going through this change. So, like we said, the Ring Nebula, so this planetary nebula specifically, is in Lyra the Harp, this constellation. It is over 2,500 light years away, and it is about 2.5 light years from edge to edge. And based on our observations of it over the last 100 or so years, we can tell by kind of working backwards that the Ring Nebula started expanding 1,600 years ago. So the next classification of nebula are formed by supernova explosions. So there are actually two types of supernovas, type 1 and type 2, aptly named. So slightly counterintuitively, we will start with the type 2, which is very similar to planetary nebulas in terms of how they form. So just to give you an idea, this supernova specifically is called the Crab Nebula. So in order to find it, we have to kind of work with two constellations. So here is the constellation Orion, and we can look at Orion's kind of sword coming up behind him, and we can make a line with these two stars and this star in the constellation Taurus. So like Taurus the bull, these are his horns, and if you extend the bottom one out, we get to this star here, and slightly to the right of it is where the Crab Nebula is. So supernovas in general come from stars 8 times the mass of our sun to 25 times the mass of our sun. So this is also when the star has reached the end of its life and turned into a red supergiant. But it's just that these stars are bigger. So as the star gets old, it cools down and then expands. And as it expands, the atoms in kind of the star's atmosphere become farther apart. So therefore, fusion happens less. So like atoms collide into each other less often. Therefore, the gravity of the atmosphere of the star overcomes the outward fusion pressure, which causes the outer layers to collapse inward. This causes the atmosphere to become dense again, which causes a new burst of fusion. And this sudden resurgence of fusion that happens causes the explosion of the star. So that's why you can kind of tell by the structure here that this has exploded outward from kind of the center point here. So the core, so remember in planetary nebulas, the core of the star turned into a white dwarf. Well, in this case, if the mass of the star was 8 to 25 times the mass of our sun, the core will be a neutron star. And if the mass of the star was more than 25 times the mass of our sun, the core will become a black hole. So this is the primary way that black holes are formed in the universe. And the gas kind of on the outside will slowly continue to expand outward. So supernova, the term was coined by Fritz Zwicky and his colleague in the 1800s. I forget exactly when. Anyway, so the Crab Nebula specifically, like we said, was located in Taurus the Bull, the constellation. The Crab Nebula is 6,500 light years away, and about 11 light years across. So you can tell that these are much bigger than a planetary nebula. Actually, so we know more exactly than for other objects, when this star exploded, because it was recorded by Chinese astronomers about 1,000 years ago. So then the other type of supernova is called a type 1 supernova, also known as a standard candle. So these usually happen when there is a binary pair of stars. That means two stars that are kind of in orbit around each other, gravitationally bound to each other. So one of these stars is a white dwarf star and a main sequence star, so kind of like our sun, maybe slightly bigger in some cases. So because the white dwarf is so much more massive than its companion star, it'll suck the atmosphere off of the companion star due to its gravity. And so as the white dwarf kind of absorbs this material from the companion star, it'll get denser and denser. And eventually it'll reach this critical density here, which will lead to fusion taking place anew. And so then, electron degeneracy pressure is a phenomenon that basically states you cannot have two electrons in the same point in space at the same time. So because of electron degeneracy pressure, and it's so dense that this is almost the case, but physics doesn't allow it to happen, that causes the white dwarf star to explode. That, and similar to the other type of supernova, that the fusion radiative energy overcomes the gravity exerted by the mass of the star. So that kind of leads to the explosion. So sometimes the companion star will survive, sometimes not, depending on how big it is and how far away it is from the white dwarf. And so these type of supernovas, type 1 supernovas, are incredibly important in astronomy because they are used as standard candles. So because we understand what's taking place when a type 1 supernova occurs, we can tell how bright it actually is. So it's absolute magnitude. Then when we see it somewhere else in our own galaxy or somewhere else in a different galaxy, we can tell, we measure its apparent magnitude. So therefore, we can compare the absolute magnitude, what we know it should be, to the apparent magnitude, what we see it as. And that lets us kind of determine how far away a galaxy is, and the speed at which it's moving relative to us. So that has led to tons of increased understanding of the mechanics of galaxies and how they interact with each other in the universe. So like I said, so these explosions are so bright that they outshine an entire galaxy, that we can see them from so far away. So you can tell this supernova happened in 2011. And so this was taken before the supernova happened, and then afterwards. So you can tell just how bright the supernovas can be. And then some supernova candidates to look out for in our own galaxy. One of them is this star called Betelgeuse. It's in the constellation Orion. It's his shoulder, the one connected to his sword, not his shield kind of out in front of him. Not this one here, but the one connected to his sword that goes up and out. So Betelgeuse is a red supergiant star, and you can tell it's a supergiant because, for scale, here's the size of the star compared to Earth's and Jupiter's orbit. So this star is hundreds of times at least the size of the sun. So we can tell that because of its size and color, it's very, very red, that it will probably go supernova. That could be anywhere from like tonight to about 1 million years from now. And when this happens, it's about, what, 650 light years away? Yep. So that means it won't, so the high energy photons that are released, like gamma rays and X-rays, will be too spread out by the time they reach Earth. And it won't be, so it'll look like we have a second sun, but it won't actually, like, we won't have more ultraviolet light coming into Earth. It's just going to be really, really bright. So then the next potentially most interesting nebula classification is a star-forming region. So an example of this is the Eagle Nebula, pictured here and located here in the sky, in the constellation Serpens the Snake. So other names for star-forming regions are diffuse nebulas and, very aptly named, stellar nurseries, because these nebulas are so big and very dense that parts of them collapse to form new stars. So the reason it has the name diffuse nebula is because it is an extremely large cloud with a very fuzzy boundary. And so, like I was saying, that they are more dense in some places than others within the nebula. And these denser places can condense to form protostars. So interestingly, this nebula specifically is where the pillars of creation come from. So they're right here, slanted slightly to the right. But yeah, that's where that comes from. So like I said, the Eagle Nebula is located in the constellation Serpens. It is 6,500 light years away. And to give you an idea for size, from one edge to the other, it is 60 light years across. So the star cluster here in the center for the Eagle Nebula is 15 light years across. And the pillars of creation themselves are 2 to 3-ish light years across. And there are over 8,000 stars in this cluster here that have been formed in this nebula. And you can tell that there is still a lot of gas yet to, that still hasn't been used up, so to speak. So there might be more that form in the future. And actually, some of you guys might be familiar with the constellation Pleiades, or not the constellation, the star cluster, the Pleiades, also known as the Seven Sisters. And this, we think, had once been formed by a star-forming nebula. And we think this because when we take a long exposure image of the cluster, we can see this gas here between the stars. And the gas indicates that there was a nebula in the cluster at some point, but since then, it has mostly dissipated. So here we go, showing an example of why having long exposure pictures are sometimes better than just the naked eye. So, like I said, the Pleiades are in the constellation, or near the constellation Taurus the Bull. Here's kind of a diagram for how to find them. The cluster is just over 400 light years away and 18 light years from one edge to the other. So the reason they're called the Seven Sisters is because there are about 7 stars visible to the naked eye, but when in fact there are 800 stars in the cluster. So we can tell that this was a smaller star-forming region, but it was caused by a nebula nonetheless. Now, this isn't a formal kind of type of nebula, but it's worth mentioning because it is gas in outer space. So we can see these especially clearly in galaxies. The kind of dust, the very dense dust that is kind of in front of the core behind us, behind kind of the dust in the foreground. So, like I said, there are usually large patches of it in the arms of galaxies. And what was I going to say? Oh yeah, so when the Milky Way, so the galaxy that we're in, and then Andromeda, which is the nearest galaxy to the Milky Way, in about 7 billion years, when these two galaxies collide, the collision of these interstellar gas regions will cause them to condense and collapse in some places and form new stars. So that's kind of the role that these clouds of interstellar gas play. So then phenomena we see in nebulas, excuse me, are these. So emission nebulas, reflection, and absorption, kind of regions within a nebula. So these aren't distinct types of nebula. They're just kind of what we see when we look at nebulas. So emission parts of a nebula are these pinkish reddish regions here. So if we think back to when I was talking about how spectra work, when atoms get excited and then they release certain wavelengths, well, so it's the same phenomenon. So this is hydrogen gas being excited, and when it de-excites, it emits this very red wavelength of light. And because the structure of the hydrogen atom is so simple, usually there's really only one kind of photon that we see being emitted from hydrogen. And that's kind of what we see here. Now, towards the center, where the star cluster is, we have what's called a reflection part of the nebula. So light from the stars in the cluster gets bounced off of the gas in the nebula, and that's why this part of the nebula looks blue, because the stars in the center are very blue, and that gas is reflecting that light. And then the last kind of phenomena we see is an absorption nebula. So there's a little bit of it right here, which is a very dense region of gas that blocks light from traveling through it. So this is kind of like what we were seeing when we were looking at the intergalactic dust, where it is so dense that it's blocking the light from being able to pass through it. So these are just kind of more examples of this phenomenon. So here is an emission nebula, and you can tell because it's very, very reddish pink. And then in here, this is a reflection nebula, kind of the blue parts here, and this is perhaps a better illustration of an absorption nebula. Because it's very dense. It almost looks black because we can't see from behind it. So that concludes my discussion of nebulas. Please do let me know if you have any questions, and thank you for listening.
Thanks, Laura. I think that was very interesting and well presented. Okay, there are a couple of questions here. One is from Carruthers, which asks, what's the best nebula we can see tonight with a pair of modest binoculars?
Oh, that's a good one. Let's see. So, well, in the early hours, you might try and find the Eagle Nebula, like if you were to get up really early tomorrow morning. So we can tell here that here is kind of what we see of the Milky Way, and that should be up early tomorrow morning. And if you can find it, it's a decent size in the sky, so it should be easily viewable. Other than that, I'm trying to think of what else might be a good target. Galen, do you know of any?
So your slide says that they're late June at 10:30 in the evening. You can certainly see the Eagle Nebula. Right now, actually, the Milky Way is very low, close to the horizon, and so there's not a lot of nebulae available. There are a lot of star clusters, globular clusters and so forth, that you can look up in the sky right now. A very good one, of course, is the Hercules globular cluster M13, and that's an excellent binocular target. But yeah, if you're interested in gaseous nebulae, best to wait about another month, and then you'll be able to see them in the evening sky. Right now, as Laura said, they're early morning objects. Okay, another question from the Fehrenbach family. If Betelgeuse exploded, would it be as bright as the sun?
So, let me come back to it. So, it would look like we had a slightly dimmer sun or a slightly brighter than normal full moon. So, kind of the in-between there. And like I said, it wouldn't be like having a second sun in that like it wouldn't help plants grow more or something. It's just going to appear like from Star Wars, Tatooine, it's gonna look like that, like we have two suns for about a month or two, and then it'll kind of start to fade away.
Right. Yeah. Thanks. And then Tony M asks, if Betelgeuse became a supernova yesterday, we wouldn't ever know it in our lifetimes, correct?
That's a good point, actually, yes, because I wrote it down. How far away is Betelgeuse? 650 light years. So if we remember, so a light year is the distance light travels in a year. So that means the light from Betelgeuse would take 650 light years to reach Earth. So you're right. So if Betelgeuse had exploded like yesterday, we wouldn't know for another 650 years because that's how long the light would take to reach us.
Right. And it wouldn't affect us in any other way either.
Right, right.
So, yeah. And let's see. From Cynthia Goldblatt, why are they called planetary nebulae?
So, planetary nebula are named for their appearance, so kind of how they appear when you look at them through a telescope. When they were first being discovered, and I forget which astronomer said this, but he said that it looked like a very faint Jupiter when you looked at one of these through a telescope. So that's the only kind of resemblance this type of nebula has to planets. It doesn't actually form from planets or have any relation to planets. It just kind of looks like one when you look through a telescope.
Right. Another question from Carruthers: would a Betelgeuse supernova affect the Earth in any way aside from being a new observational target?
Yes, so that alone would be really, really interesting, looking at it and the nebula that it would create. But otherwise, no, we wouldn't get any high energy photons from it because they would be too redshifted and too spread out. So we wouldn't be able to see that. And like I said, it wouldn't help plants grow any better. You wouldn't have to worry about putting on extra sunscreen. It would just appear that we have another very, very bright object in the sky.
Okay. From John Affleck, how often do astronomers discover new nebulae?
So we don't discover very many new nebulas within our own galaxy, because we generally have a very kind of up-to-date catalog. So the new kind of the most updated that we would see of any of these objects would be supernova explosions such as this one here. So we can tell, and this is actually kind of citizen science, where people, maybe amateur astronomers that like to do astrophotography, could maybe take a picture of this galaxy and say, hey, this star looks really, really bright. Did it go supernova? And they can kind of submit it to a database, and then scientists can determine, oh yeah, this is a supernova, or no, something different happened. Or no, maybe it's just you, something weird happened when you were taking the picture. So the most kind of new discoveries that are made in terms of nebula are usually supernova explosions, such as these.
Yeah, I think that's fair enough. There have been cases where people have found new objects that are very diffuse and just simply hadn't been noticed before. But yeah, I think in general you're right that that new nebulae in our galaxy are unlikely to be found except for when some star in our neighborhood ends its life and becomes a planetary nebula or a supernova or something like that. Mm-hmm. Okay, from Charles. How would Betelgeuse exploding affect animals that use the moon to guide them like moths?
That's a really interesting question. Yeah. So sea turtles is another example that would come to mind. My guess is that they would probably be thrown off a little bit, because Betelgeuse would be so bright. So depending on where it is in the sky, like if Betelgeuse appeared to be on the opposite side of the sky as the moon, I imagine these animals would be very confused. Although, because I think, if I understand correctly, that these animals they don't say, oh, that's the moon. They just see, hey, bright light, let's follow it. So I think they wouldn't be able to kind of differentiate and determine which one to follow. So I think, yeah, that would probably be very confusing. But like I said, this would only appear to be this way for a month or two. So hopefully it wouldn't throw things off catastrophically.
Okay. So related to that is, do any historical documents that recorded supernova, like the Chinese one, also discuss the effects on nocturnal wildlife?
Not that I know of. I could be wrong, I could be missing something, but to my knowledge, I don't think so. Do you know of any, Galen?
No, I don't. It might be interesting to look up some of those old documents and see, but yeah. And then, yeah, how bright, from the Fehrenbach family, how bright was a supernova in 1054? Was it something like a second sun?
Probably about that, or maybe slightly dimmer than a full moon, just because this supernova was, or actually no, I take that back. So this supernova, the Crab Nebula, is 10 times farther away than Betelgeuse is. So if we think about it, it would be very, very much dimmer. But
100 times dimmer.
Yeah, but it would probably be about as bright as Venus, or the bright star Vega in the summertime or the bright star Sirius in the wintertime, probably be kind of around that brightness. And therefore, people back then were probably thinking, wow, this is new and interesting. And that's probably why they recorded it.
Right. Yeah, I think it was visible in the daytime for some months, so it would have been considerably brighter than Venus.
Oh, okay.
But then Betelgeuse being 10 times closer would be, considerably, brighter than that.
Right.
So, sort of, yeah, -10 or something. Let me see. Was the supernova seen by the Chinese 1054 the same one that is thought to be recorded in Chaco Canyon?
I'm not familiar with that, so
okay.
I don't know.
I think the answer is yes. There is a question about that, and the talk that we did a couple of weeks ago on the brightness of the night sky. Phil Lipscomb pointed out that there was this pictograph in Chaco Canyon that seems to have indicated a supernova, and the thought is that was the 1054 event. And I think we'll hear some more about that next week, because Chick Keller is going to be talking about some archaeoastronomy things that most probably including including the Chaco Canyon pictograph. So in fact, I think that's the preview slide that was on the website. So yes, come back next week and we'll hear a little bit more about that. Let's see. Why do we see, from Carruthers, why do we see so many different shapes of nebula? What determines the shapes we see?
Interesting. So let's go up. Nope. Here. So most planetary nebulas look the same, kind of this ring shape. Most supernova generally look the same. I mean, they have slight variations, but you can kind of see that they have more dense regions of gas than others, and they're roughly round. The most variation we see in a nebula would be in a star-forming region, like the Pillars of Creation, like the Eagle Nebula, and like the Orion Nebula. So that has to do with how these nebulas formed, which I'm not too certain of. I can talk about it kind of in general terms. So these nebulas are much bigger than supernovas and planetary nebulas. So their structure has much more room for variation, so to speak. It also has to do with, like, we can see in the Orion Nebula specifically that the cluster of stars in the center has kind of pushed out the gas that was that had formed the stars originally. So this nebula was much more kind of compact in its early days of formation, but the cluster has since pushed outward on the gas. And so I think the structure of the cluster probably also has a lot to do with the current structure of the nebula. Galen, do you have anything to add?
Yeah, if I can just say that the structures of emission nebula in particular are very varied, and that in part reflects the dynamics and turbulence of the interstellar medium. Things are, there's shock waves bouncing back and forth, and these ionization fronts going out, and all of this, just a very dynamic. It happens slowly as far as our eyes can see, but these things are, there are motions out there that are measured in tens and hundreds of kilometers per second, and it's a very violent and dynamic environment that these things are formed in, and so you get lots of different shapes. So, you know, as you say, the planetary nebulae are rather more simple because there's just an expansion from a center. Likewise, a supernova, except that the supernova is much more violent, and so you get all these crazy filaments and stuff inside it. But yeah, I mean, we try to understand these things in terms of the motions of the gas and the interaction between the radiation that excites the gas and the gas itself.
Mm-hmm.
Okay. So one thing about planetary nebulas that Rick Wallace just reminded me of is that once our planetarium reopens, which I don't know when that's going to happen, but hopefully sometime in the not too distant future, we invite you to come and we'll take you on a tour through a handful of planetary nebulae where we can actually fly through them and get a full three-dimensional picture of them, and so that will be a lot of fun. But we have to wait until we get clearance to open the planetarium again. Let's see. From Charles, do nebulas create new elements like iron or carbon?
So during supernova explosions, especially, okay. So as the star gets old, it expands outwards, and then gravity takes over and collapses the atmosphere back inward, and then there's a new burst of fusion, so to speak, because it's all very dense again. So in that, and I think it happens in a matter of seconds, that the explosion it happens because all these new elements are fusing very, very, very quickly. And so that is how you get heavy elements past iron, and even some other like carbon and oxygen and some other ones like that.
Yeah, very good. It's in the supernova explosion itself that happens. Does anybody from the audience want to add anything to the story that Laura has been telling this evening? If so, raise your hand and I'll unmute you. No, I don't see any. And so we're coming on close to 8 o'clock. Used the better part of an hour here, and I don't see any more questions coming up. So I think we'll conclude our presentation. Thank you all for joining us. Thank you especially, Laura, for putting together this very nice presentation. And as I said, next week we'll have Chick Keller telling us about some archaeoastronomy sites in the Southwest, and we'll be doing a little bit of exploring of, I hope, of the Chaco Canyon, and also some sunrise and sunset and solstice and equinox markers that are within our area. And finally, just another question: will this be available on YouTube? Well, we'll see. I've made a recording, and we will look it over, and if it's okay, we will put it up on YouTube. Anything else? Any other questions? No, I don't think so. Well, thank you all. We had a total of a maximum of 26 participants this evening, which is pretty good. And like I said, join us next week and in subsequent Friday evenings for future presentations. And we hope we can invite you all back into the planetarium in the not too distant future. Thanks once again, Laura.
Thank you guys very much for listening.
Right. Okay. Bye-bye, everyone.